So the journey actually took about 25 years from the moment of I can make an efficient OLED to million people using Samsung Galaxy phones to go ahead and demonstrate the value of this technology. The challenge of this technology, though, was that it's utilizing materials never before used. It's utilizing them in a format that has never been previously done. As a matter of fact, the materials it's using, the carbon-based materials, have been universally maligned as unstable, as easily oxidized, as hard to process, as impure. Gosh, why would you ever, as an electronical aficionado or electrical engineer or scientist who wants to make this thing really work well, why would you ever even look towards these materials as a way to go forward? Silicon is your answer. Well, it doesn't glow. Okay, let's find something else that glows, but it has to be silicon, right? Because that's we understand. The challenge of OLEDs actually tells a tremendous amount of insight. When you look at that Samsung flexible OLED screen, there is something truly unique about it, which is that it's a screen that bends. Do you ever need it? Actually, you don't. No, you never read your newspaper bent. You always hold it as flat as you can, right? So if you ever read newspapers anymore. But the reason why I went with a newspaper is to show you that here's an object I'm hoping can be flat for me to read it. So what the heck could possibly be the value of a flexible display? That's ridiculous. And it's not the flexibility that's valuable. It's the thinness of it that's valuable. As a matter of fact, most of us don't remember, but some might, when the first time liquid crystal displays were introduced into the world. There were these huge boxes called CRTs, and now we're going to have these flattish, like an inch or 2 inches thick screens called liquid crystal displays. They looked horrible. Like you look at the screen, you're like, I can see it's a picture, but it's not really very colorful. It kind of lags, like there is a blur of the image, but man, is it nice because it's thin. And you're like, why does that matter? That's not the picture. That's not the screen. That's not the value of the screen, except it is. That's what consumer really wants. They want less space in their room occupied by a box that is a TV. They want the ability to add it to an electronic box and make it into a laptop. They want it so thin that it's imperceptible, if at all possible. And that's the wave that OLEDs took, except OLEDs returned the quality of the color, made them more energy efficient, and also gave them that extreme thinness. But it required an entirely new material set. And so here is the awesomeness of OLEDs, or quantum dot LEDs, that I'll mention in a moment, which is the power consumption per inch squared dramatically reduced compared to the standards. Else liquid crystal displays, plasmas, rear projection TVs, these are ancient beasts of the times past now, but were the standard ways to display technology 10, 15 years ago. OLEDs had these advantages of high contrast, super thin, ultra fast, pure color, curvable, with the one significant deficit. They require a large area nanofabrication technology. So present this to any rational technologist, and they'll say, well, it'd be really nice to make OLED displays in a large pixelated format, but since I know the industry, I'll tell you this. Apparently, every one of those 4 million pixels needs to work. Well, that sounds like an obvious statement to you and I, because we expect TVs to have every pixel that works, but that is not the way electronics works. Inside your chip, like M2, M1, that is running your laptop in there, 10% of transistors do not work where you expect them to work. 10%, sometimes 20%. When you're like going to a store and you're buying a 3 gigahertz machine or a 2 gigahertz or a 1 gigahertz machine, no one ever intended to make the 1 gigahertz machine. That's the machine with a chip that has many bad transistors. And they slow down the chip so that you don't see how badly it will perform at high speeds. That's the way to use the deficit of the ability to actually make absolutely perfect every pixel working. And I'm going to now tell you, now make me electronics technology that has never been made at the yield that I need for the display. Oh, and by the way, your eye can pick 2% difference in brightness between neighboring pixels. So every one of these needs to work to within 2% accuracy of each other. Again, never done before. At the yields never done before, with material that has never been used before, at material thicknesses that are way thinner than the critical dimension of any previously made electronics technology. Oh, and by the way, your chip is not 1 by 1 inch in size, but it's going to be 2 by 2 meters in size. That's ridiculous to even attempt making a machine for. But if you're an MIT student, the answer back to me is, well, is it impossible? Well, no, it's not impossible. But it's highly unlikely that you're going to get all of those milestones met. And consequently, in a rational world, I'd say, don't bother. Except you look at the enthusiasm of students, and they're like, well, is it impossible? We can go and calculate, is it ever possible for us to do this? And calculations tell us, yeah, it's doable. There is nothing really, really stopping us except it's never been done. So they make things like this. They launched a company called Cativa. Cativa was launched in 2008. And by 2016, December 2016, their tools were in factories in Asia. This is a small version of their tool. This is a printer. It's using a 2 by 2 meter piece of glass. And it has this glass sliding back and forth. That print head has 1,000 nozzles. They are covering the entire area with active polymer or passive polymer, depending on what's needed. It's primarily used these days for encapsulation, extremely accurate encapsulation tool sets. It can deposit quantum dots. It can deposit molecules. It can be used, as it's being used right now as well, for OLED manufacturing. And by the way, that whole area of a 2 by 2 meter piece of glass, you have 75 seconds to cover it with a layer of material. With a 25 micron positioning accuracy, few nanometer thickness accuracy, 5 micron definition between lines. Every one of the pixels needs to work. Sounds impossible, but if you have enough cleverness in the way you've designed this, understanding of materials, and then also software that continually monitors what you've done and adjusts on the fly for the errors that you make, you can make an extremely powerful machine. Cativa's tools in just the first year of operation encapsulated 100 million cell phone displays. And the tool I'm showing you there is one of these early ones, like roughly the Whitney one up there. Actually, I'm sorry. Yeah, between Shasta and Whitney is the one that I just showed you. They use different peaks in California mountains to name all their machines. And as the time went on, they done better and better. Today, they are the leading supplier of inkjet equipment to OLED display industry. If others have tried copying their tool sets, they require 10,000 different parts providers that need to work just right in the just right way. And others who have tried copying their machines have not succeeded because of everything that takes to actually make it work. But the company now employs several hundred people that are over in Newark, California, just north of San Jose, that is developing these for whoever needs them, and many people do need them. They are looking at other ways of branching out in new types of technologies. It's a story that I would never tell you ever to try to attempt to reproduce, right? Because it's one of these, like, it is so hard to make a foundry for new materials, but they've done it. And although I've told you I would never tell you to try to reproduce it, here is another story of reproducing that very same idea, but now in a different material space called colloidal quantum dots. Colloidal quantum dots themselves are beautiful to electrical engineers like myself. I love the fact that you can choose the size of the dot and not change the chemistry of it and still get a different color. I love the fact that I don't have to know too much chemistry. As long as I can stick with one chemistry, I can get to places to actually make things really work for me. It also is tremendously satisfying to have really good colleagues. And since I joined MIT, I worked extremely closely with Munjiba Wendy. You might have heard of him. Recently, he won the Nobel Prize in Chemistry for colloidal quantum dot synthesis. The beauty of the work is that the journey did take about 30 years to go from the basic discovery of glowing dots to the scale up of those glowing dots in a practical technology. And let me show you some of those practical technologies. Back in 2009, they made the very first really good-looking light bulbs. Now, they were upped by one other company before them who made Christmas lights that put a little quantum dot on top of a LED to make different monochromatic Christmas lights. But, you know, that's cool. But what was cooler was to be able to look at the incandescent light bulb, realize that a cool white LED that was made at the time, illuminating a bowl of fruit, would make your bananas not look so appetizing. However, if you take a cool white LED and add to it a thin layer of so-called QD optic, you can generate the perfect glow of an incandescent light bulb. Brian here might know a little detail or two about it because he was in the middle of that story. But 60 lumens per watt is about 5 times more energy efficient what an incandescent light bulb can do. And yet, from perspective of a user, looks exactly the same color-wise. This is a way of rethinking what a light for you does. 20% of the world's electricity is used on lighting. If I can reduce that by taking LED lights and maintaining the quality of the light, people will be much more likely to adapt it. And I can save a whole bunch of energy otherwise that would not be, otherwise saved. The opportunity is very large, but you need to make a business out of it. And for as awesome as Q Division's vision was, as a matter of fact, this was the very first pivot of Q Division, the little startup that commercialized this technology starting in 2005. Their very first picture of who they are is a company that's going to replace OLEDs using the quantum dots as the light source in an OLED. The thing we missed is that there are no foundries for OLEDs or QLEDs back in 2005 when we started this. Cativa did not make their first tools yet. Cativa didn't even exist. They incorporated 3 years later. And Cativa's demonstration of a quantum dot printing, that just happened over the last few years. So the ability to actually make a pixelated display out of quantum dots, yes, I can do it, but I needed the tools that Cativa has now in order to use the chemistry and materials that Q Division developed at the time. Timing is everything, and having that full vision was really important. So Q Division recognized that this is indeed not going to work quite well for electrically excited quantum dots and said, well, what if we do optically excited quantum dots? We can use gallium nitride LEDs that are electrically excited and absorb the blue light from the gallium nitride and give you the light of the quantum dots optically excited. It works extremely well. The dots last forever. There is nothing that kills them, it appears that way. Electrically excited dots don't last forever. I'll tell you at some other point if you really want to know why, but optically ones, amazing. Great mix. Fantastic business. Economist writes a story about you. Boy, are you flying high. Light bulbs at the time were costing about $20 to $40 a light bulb. That's great. All I want from a light bulb maker is to give me 5% of the value of the light bulb, right? You get $2, so give me 10 cents and I'm fine, right? $20, give me $1 and I'm fine. That's all I want. But the problem is this second story, which is that the light bulbs went from $20, $40 down to $2. And what used to be $1 per optic dropped down to 10 cents or 5 cents an optic. I can't make a business out of it. I mean, waking up in the morning and picking up a box of optic, that costs 5 cents, right? If not much more. I can't make the business out of it. I need more expensive light bulbs to make. So the brilliant scientists and engineers and business people at Q Division said, well, every TV, like this one, or a screen, has a light bulb behind it. Those are more expensive than a couple of bucks a piece, because you're selling the screen for $100, $1,000, right? I mean, I can ask you for like $20 to pay for a good-looking light bulb, especially if I can replace the light bulb and make your TV look better. And that's what they've done. They replaced every white light bulb behind an LCD screen with a light bulb that had a blue emission from gallium nitride, very sharp red emission and green emission from the quantum dots. Now you had a perfectly saturated blue, green, and red shining through your liquid crystal display filters, and as a result, the colors you were seeing out were also pure and saturated colors. Take my light bulb, put it in your today's LCD screen, and you'll make your LCD screen look way better. Well, that's an edge that many of the display makers would like to have over their competitors. And in 2013, Sony introduced, it actually introduced the so-called triluminous quantum dot enhanced LCDs, showed it in January 2013 at the Consumer Electronics Show. They won the best TV of the show. The world was going to, from now on, know that what the world needs is a quantum dot enhanced TVs. And QDivision will be a successful company that will forevermore be known as the one who introduced and pioneered and grew the quantum dot industry. Now, that's a great story to tell, right? It didn't quite work out that way. It didn't quite work out that way because there are business pushes and pulls. The moment you start being successful, you're in the target of everyone else. And all the other guys would love to buy you, but not for very much money if they can. Next 3 years that followed were not a Cinderella story of QDivision. It was actually quite a bit of a struggle between different makers who wanted this and that, between other quantum dot companies who felt that QDivision has infringed their patents, despite the fact they didn't, but sue them here and there, because they now might have money coming from Sony, so maybe they can pay. The best thing to do in those cases is either fold or look for the next best opportunity to give to the world. And in this case, it would be to ask Samsung, or Samsung asking you, do you want to be bought? And you might as well. You're struggling in every other way to survive. QLED technology that Samsung introduced is originated from the QDivision's vision of what they've done. And QLED technology today, after acquisition by Samsung, is about $4.5 billion industry. That's good and is growing. Every TV that you go into Best Buy and look for, if you look at the best looking TVs, they're either QLEDs or OLEDs. They are the ones that give you most lifelike images. And quantum dots are truly remarkable in the way they're operating right now. The latest version from Samsung actually combines an OLED with a QLED. A little bit of a crazy technical idea. They use blue OLEDs and put quantum dots on top to make them beautiful colors. We can discuss, is that good or bad idea? But from perspective of beauty, it's an incredibly powerfully looking TV, enabled by the vision of what QDivision did and what the MIT labs initiated. And what those crazy students that said, we're going to scale up the making of the quantum dots, never done previously at the scale. Well, we can do it. We can do it.